Hello everyone, my name is Alal Amir Ahmad. Welcome to my presentation about joint association and beamforming optimization in multi-cloud radio access networks. This work is jointly done with Haytham Dahrouj from Ifat University, Anas Shaban from University of British Columbia, Aidel Sisgen, my supervisor from Ruhr University Bochum, Tariq Al-Nafouri and Muhammad Salim Alwini from KAUST. Here is an overview of the talk. First, we show why multi-cloud RAN are essential for managing modern communication networks. After that, we introduce the system model and the associated optimization problem. An iterative algorithm based on fractional programming approach is then introduced, followed by the numerical results, and we conclude by summarizing the main points of the talk. 5G networks are characterized with many factors, but perhaps the main innovation brought by 5G networks is the ability to provide a flexible platform for heterogeneous sets of applications and services with different requirements. In this figure, we see that these services and applications can be classified into three main categories. For example, all the services within enhanced mobile broadband category require high data rates, while the services within the mission critical control require rather ultra low latency communication. Obviously, the ability of beyond 5G networks to support such a heterogeneity in services and requirements distinguish it from previous wireless communication systems. To realize the vision of beyond 5G systems, next generation of communication networks is expected to be ultra-dense. Spatial reuse by deploying more and more base stations can boost the energy and spectral efficiency of wireless communication networks. In this context, cloud radio access networks are proposed as a practical network architecture to manage and control such ultra-dense networks. In CRAN, we can mitigate the interference by establishing cooperative transmission schemes between different base stations, and we can make use of advances in cloud computing technology to allocate resources in the network efficiently. The majority of works in the literature focus on single cloud model. As we see in this figure, according to this model, all the base stations in the network are connected to a single cloud via limited capacity front haul links, while in the cloud a pool of baseband processing units is responsible for managing the network. However, this model poses serious challenges in practical systems. For example, according to a single cloud scenario, one central processor at the cloud is responsible for managing a massive number of network nodes, which can be actually very complicated in practice. Moreover, the single cloud scenario can be even infeasible in practical systems due to the geographical location and distance constraints. Multi-cloud radio access networks address the challenges arise by single cloud model by distributing the intelligence across multi-core architecture. With this structure, we can design efficient and distributed optimization algorithms with a small communication overhead between the clouds. Here is a configuration overview of the studied multi-cloud radio access network model. In this model, each cloud is responsible for managing a sector in the network, and a sector is characterized with a distinct set of base stations. The clouds are allowed to communicate with each other. For example, this cloud can communicate with this cloud, but they can only exchange control information, not users' data. The user's data, for example, of the users associated with this cloud can only be shared with the base stations connected to it, for example, this base station. And that's why in our model, each user can be can be assigned to one and only one cloud. Based on our discussions of system configuration in this work, we assume a pair base station maximum front haul capacity constraint and transmit power constraints. Besides, each user is allowed to be associated with one cloud at maximum. The goal is to maximize the achievable sum rate of all users across the network by jointly optimizing the aggregate beamforming vectors of all users and the user-to-cloud association variables. Let ZCK indicate the binary variable of associating user K with cloud C, while WCK refer to the aggregate beamforming vector of cloud C to user K. Moreover, let HCK refers to the aggregate channel vector from cloud C to user K. Then we can define the signal to interference plus noise ratio of user K when associated with cloud C as such. This expression accounts for the connectivity constraint by explicitly writing the association variables in the expression of it. Plus, also it accounts for the intra and inter-cloud interference terms, as we can see here. And this makes our problem a bit different from conventional SNR expressions, where those expressions usually are only a function of beamforming vectors, not of the association variables. Now we are ready to present the optimization problem we are interested in. As discussed previously, we are interested to maximize the achievable sum rate of all the users across the network. We note that the sum here is taken over all possible associations between users and clouds. So this is the associations here. And the first constraint represents the achievable rate constraint, which link the SINR signal to interference plus noise ratio of user K when associated with cloud C to the achievable rate of user K when associated with cloud C, where B represents the transmit bandwidth. So now let WCKB refers to the beamforming vector of base station B in cloud C for user K. Then the maximum transmit power constraint for base station B can be defined in this equation here, where ZCK refers, of course, to the association variable between cloud C and user K. The maximum front haul capacity constraint is given here, where this function is actually the indicator function, which means this function is 1 when user K is connected with base station B in cloud C and 0 otherwise, because the rate of user K contribute to the front haul link of base station B only if it's connected to it. Otherwise, we don't need to account for that. And finally, the binary values of association variables. We know that ZCK is 0 if user K is not connected to or not associated with cloud C, and 1 otherwise. First, we recognize that our optimization problem falls within the class of sum of ratios optimization problem, which is given here in its general form. In general, this sum of ratio optimization problems are non-convex, but by using fractional programming techniques, we can transform it into this form, where ym are actually auxiliary variables. The advantage of such a transform is that we can use convex approximations technique to solve the problem in an iterative manner efficiently. Using fractional programming approach, we can solve the joint association and beamforming vectors optimization problem by decoupling all the association variables in the objective And more importantly, it enables the distributed implementation of the algorithm with reasonable communication overhead between the clouds. The optimization problem we've studied is non-convex because the feasible set is not convex, which can be visualized in this figure. The solution starts by approximating the non-convex feasible set around a feasible point here. So we establish the convex approximation represented by this convex set. You can see it's a convex feasible set. And since it's convex, we can solve it efficiently. So after solving it, we get the next approximation point. The next step is to start from the previous optimal solution and build the next convex approximation, which is shown in this convex set. So after solving it, we get the next approximate point represented by this point here. The process continues until we get a convergence here, and we declare that as an optimal solution to our problem. We consider a communication network as shown in this figure. Both base stations and users are uniformly and independently distributed across the network, and we assume that each base station is equipped with 2 antennas. The network area can be divided into 4 sectors where each sector can be managed with 1 cloud. In 4 cloud scenarios, we have Cloud 1, Cloud 2, and Cloud 3, and Cloud 4. However, in 2 cloud scenario, we have Cloud 1 and Cloud 2 merged together, and we merge Cloud 3 and Cloud 4 together. In the first scenario, we plot the achievable sum rate of all users across the network as a function of front-haul capacity per base station in different setups. One cloud setup refers to the case in which the whole network is managed with 1 cloud, which is infeasible in practice and serves here as an upper bound on the performance of multi-cloud setup. We distinguish between centralized implementation, where the clouds fully cooperate to optimize the beamforming vectors of all users, and the distributed implementation, where the clouds design the beamforming vectors locally and exchange interference information only. Obviously, the joint optimization of beamforming vector and association variables outperform the scheme in which we optimize association variables only, as we see here. And we also note that 2 cloud scenarios perform better than the 4 cloud scenarios as we come closer to the upper bound. However, we shall keep in mind that implementing 4 clouds in practice is more feasible than implementing 2 clouds due to the distance and geographical location constraints. In the second scenario, we plot the achievable sum rate in different cloud setups as a function of users' density in the network. Interestingly, the performance of the distributed implementation becomes closer to the centralized one as the network becomes dense. This indicates that in dense networks, even with partial cooperation between different clouds, we can achieve a good performance and in the same time save much in optimization complexity. In this work, we study the multi-cloud radio access network setup. In multi-cloud radio access network setup, it becomes essentially to jointly optimize users to cloud association variables and the aggregate beamforming vectors of all users across the network. We have also studied fully and partially cooperative schemes between the clouds. And interestingly, in dense networks, we noticed that practical multi-clouds with partial cooperation can achieve a good performance compared with the theoretical upper bound schemes and centralized schemes. Thank you for listening. I will be happy to answer your questions about my talk.